Hi everyone, welcome to my channel and welcome to a new video. So in this video we'll be looking at a few very basic stuff related to file reading and writing, basically file operations in Linux. I'm calling them basic, but they are not only basic but they are very core to doing file operations in Linux and how file operations actually work in Linux, right? These things always help us better understand how the kernel works when it comes to reading, writing files, operating on files, and also it helps us to debug things when something is not working as expected. So we'll be discussing things like file descriptor, file description, which sounds very similar to file descriptor but it's completely different, and primarily inodes, right? So yeah, without further delay, as always, let's get started. Okay, so here I have a tiny snippet of a C program which mostly reads from a file, and so I'll be using these snippets to explain whatever I want to discuss in this video. So what is a file descriptor, right? What is a file descriptor and how is it used? So we all know that in order to do anything in Linux with files, be it a socket file, a pipe, a disk file, we have to get hold of something known as file descriptor, which is nothing but an integer, right? If you want to open a file in Linux, for example, this file that I have created here, hello world file t.txt, and there's a tiny program f.c which tries to open this file in using three different approaches. When we want to open this file, we use the open system call, and all that the open system call returns us, if everything went fine, is an integer, right? And that's called a file descriptor. So, and after that, whenever you want to do any operation on that file, like reading from the file, writing from the file, unlinking or deleting the file, for each and everything you need this file descriptor. But how does it help the kernel to know which file we are talking about, right? How does it help the system calls to know which file are we talking about? Why is this file descriptor so powerful, so important that it can give you various informations about the file, right? So to understand these things, we need to see something for ourselves first. So here I have a simple, as I said, it's a simple program. So the first function, let's go one by one. So in the first function, it's a pretty basic file open and read. So I'm opening the same file t.txt two times. So once I'm getting fd1, once I'm getting fd2, right? So as we know, the number of times you open any file, be it the same file, you get different file descriptors, as I was just saying a few moments back, and these file descriptors are in the increasing order. Every time it's guaranteed that the lowest possible file descriptor is returned to you per process, right? So the file descriptors that's always open for a process, the moment it gets created, is fd012. So mostly this fd1 will be nothing but 3, fd2 will be nothing but 4. And then what I'm doing is I'm trying to read from this using this fd1 twice. So here I have defined a buffer of 10 bytes, and first I read 1 byte using fd1, I print it, and again using the same file descriptor I read another byte, right? I read the second byte from the file, and once again I print it. So first two times I'm using the same file descriptor, and the second time I am using fd2, right, to read 1 byte and print it out. Pretty simple. So let's see how it behaves, right? So I'm calling it separate open because it's opening the same file twice separately, and let's try to run it. So I'll first compile it and then I'll run it as expected. So we got the first file descriptor as 3, then 4 from fd11. So the first two times I used fd1, it read h, and then the read operation, we all know that it will move the seek pointer, the file seek pointer by 1 byte. It will move the file seek pointer by the number of bytes that were read. So it moved it by 1 byte, and when we call next time, when we call read system call next time on fd1, it gave us the next byte, which is e in this case. And similarly, when we used fd2, it was at the beginning of the file, right? The seek pointer was at the beginning of the file, and it gave us the first character h. These two fds are completely separate from each other, and it worked as expected, right? Let's go to the next example and see what's happening there. So in the second example, or in the second function, what we are doing is we are opening the file once. You see, we have used the system call open only once, and we got back our file descriptor, and now we are duplicating or replicating this file descriptor using the dupe system call. So what the dupe system call does is it takes an existing file descriptor and it duplicates it, right? It creates a new FD, which means this FD2 will be will have a different value than this FD1. So this will be 3 and once again this will be 4. But both of these file descriptors are pretty much the same file descriptor, right? FD2 is simply a clone of FD1. So how do you think? What do you think this time it will behave? Like how will FD1 and FD2 behave? So in this example, once again I have a buffer of 10 bytes. I am trying to read first byte from FD1 and second byte from FD2. So by first second byte I mean the first instance of read system call uses FD1 and the second instance of read system call uses FD2. And remember, both the times same file, once again t.txt, same file. This time one file descriptor FD2 is a clone or a duplicate of FD1, right? So let's see how it behaves. So what I'll do is I'll simply do a copy and I'll do a paste here. So once again I compile. Okay, so remember how this time when the file descriptor got changed, FD1 and FD2, the offsets were maintained independently. Although FD1's offset in FD1's seek pointer or FD1's file offset increased and got incremented to the next byte after reading the first byte, but for FD2 it stayed at the first because this is the first time, like this instance is the first time we read from FD2. So for that it still was the beginning of the file. But in this case, although we read 2 times from 2 different file descriptors, FD1 and FD2, since they were the clones of each other, the kernel did not maintain different offsets for us, right? It didn't maintain different offsets for us, but even the offset was shared between FD1 and FD2 because FD2 was created using dupe, the dupe system call. So when I called first time on FD1, the read system call, it returned me H. It auto incremented the offset to the next byte. And even though I called read system call on FD2, it gave me E because it read from the new offset, that is the second byte. So here is our major difference, the first difference. How did the kernel do this? How did the dupe system call actually work, right? How did the kernel keep track of the fact that FD2 is simply a clone of FD1, but in the first case, it knew that FD2 and FD1 is different, not the same FDs. How is the kernel doing this? So this kind of gives us a hint. The kernel is maintaining some data structure which is keeping track of the offset per FD, right? So it knows even if the file is same, for which FD what is the offset. If one FD is a clone of the other FD, it knows that the offset is same for both those FDs. So the kernel very smartly is maintaining some data structures in the kernel which lets it keep track of this thing. And next go to the last example now. So it's pretty much like dupe, but the approach is different. What we are doing here is, so first in parent, we are once again opening this file t.txt. Now once we get this file descriptor FD1 from opening t.txt, what we are doing is we are forking a child, right? So here we are forking a child, and what the child function does is it simply takes this FD1 as a parameter, right? So if it's a child, we are running this worker function, and which takes this file descriptor FD1, and what it does is it simply again reads 1 byte from the file, right? It reads 1 byte from the file and it prints it, and then it waits for the child to exit. And once the child has exited, what the parent does is it also reads 1 byte from the file right here using the same file descriptor FD1, and it once again prints the read value, right? It once again prints that 1 byte that it read from the file using this file descriptor FD1. So let's see how this one behaves. So what I'll do is I'll copy this parent function and I'll put it here. Once again I'll compile the code. So the first thing that got executed is a child. So that's why it says in child FD received from parent is 3. So that's the FD that the parent got when it called the open syscall, and then it read the first byte, which is H. And in parent, when the parent used its FD, that is FD1, and it tried to read something, it got the second byte, that is E. So it might seem that we are passing the same FD1 in this case to the child, but it's not the same FD. fd1, or it's not the same file descriptor that the child is getting, right? It's getting from its parent, but it's not this exact fd1. The reason being, in this portion of the code, this is no more the same parent process, right? This is not the same parent process. This part is again the parent process, but this part is not the parent process, it's the child process. So at this point, the child has been forked and the child is receiving a new file descriptor, which is a new file descriptor only in name, because it's a clone of parent's file descriptor. But again, it's the distinction that we need to make here. It's not like passing the same file descriptor over a normal function call in the same process. It's a completely different process which has been forked from the main process, which also means what's happening is pretty similar to dupe. The fd1 once again got duplicated from the parent process to the child process, and the child is working on the clone of fd1, right? This would have been a bit different if while creating the file descriptor using OpenSys call, we would have mentioned close on exec. So close on exec is a flag which makes sure that if in the new child process you do a exec, just before the exec call is being made, the file descriptor which the child got as a clone of the parent's file descriptor, that gets closed, right? If that file descriptor had that flag, the file status flag, close on exec. So this is one more example where the file descriptors are different, but actually they are clones of each other, and the kernel knows that since these two file descriptors, even though they are different, they are clone of each other, the offset needs to be the same for these two file descriptors, right? They cannot be different. But when you are doing two different open calls, what we are seeing is that the two different file descriptors that we are getting is very much different from what dupe is doing, and the kernel is maintaining different offsets for those two different, individually different offsets for those two different file descriptors, which brings us to a very common pattern that we are observing here. If the individual descriptors are coming from two different open syscalls, right? If the file descriptors are coming from two different open calls, the kernel is able to maintain the offsets separately, right? And the reading is happening from different offsets. fd2 can proceed, fd1 can, if let's say you read 1 byte from fd1, 2 bytes from fd2, it means fd1's offset will increment by 1, fd2's offset will increment by 2, and so on, right? So the key pattern here is that if we are using a new instance of OpenSys call to get a file descriptor instance, then we are getting a per file descriptor new offset, right? Otherwise, if the open call, the original open call from which we are getting the file descriptor is same, and we are doing things like forking of process or duplicating the file descriptor, the offset that the kernel is maintaining for all those file descriptors is same, right? You read from one descriptor, that will also increment the offset for the other file descriptor, right? So this is the core pattern that we are observing. So now that we know about this behavior of file descriptors and the OpenSys call, let's try to understand why this happens and what is a file descriptor in reality, and just from an integer, how is the kernel able to figure out, or the system call able to figure out which file to access, which blocks to read from, and all those things, right? So let's go a level below. So when a process, let's say there is a process P, let's call it P1. Let's call this process P1. And what this process does is it opens a file called, using the open system call, it opens something called t.txt, right? And we also give it a flag called ord only. So there is a status flag that we are passing along with the actual file path to open system call, right? So what actually is happening in the system when you are opening this, every running process has actually got a table to track open file descriptors. It's called the open file descriptor table. So the table looks something like this. So it's basically an array, right? We are calling it a table. And so in the array, consider it as an array of structs. So among the other properties of the struct, or you can call it a column, one column or one property is file pointer. And this is extremely important, right? What is a file pointer? And in that table of this open file descriptors, right, we need like every array has got an index, right? So the other columns can be fd flags, right, and things like that, but we are not interested on those. We are only interested in this column, which is file pointer, or this property of the data structure that is used to store these rows, that is file pointer. And like every array has got a index, right, like an index number like 0, 1, 2. It's a pure normal array. Now this index for a process inside a process's open file descriptor table, these indexes is what we call in a fancy way as the file descriptor number, or basically the file descriptor or open file descriptor, right? So what we get from open is nothing but the index value of this array at which this new file descriptor gets entered. If I call another open function call and the new file descriptor entry happens at this position, that at 4, and there is some file pointer again, let's say this one is 20, 21, 40, 42, 43, right? So what we will get back from open is basically this index value of this table, also known as the file descriptor number, and that basically becomes that integer which we refer to as FD from the return of open. So in short, FD is just not a random integer, but it's actually the index at which that file descriptor entry was created in the open file descriptor table of a process, right? That is actually your FD. So coming back to this file pointer, what is this file pointer? So the kernel maintains a system-wide table of open, or also known as open file table. It's a system-wide table to track all the open files in a system. And this looks something like this. Again, this is an array of structs, and there are various fields, but we will just pick a few. And this is where we need to observe certain things very carefully. Here we have a column called file offset, right? And this is slowly bringing us near to our question, how the kernel is able to maintain different file offsets for different file descriptors for a given file. So we have among the many other properties or columns, I'm simply using this property and column interchangeably because it's at the end of the day it's an array of struct, right? In struct you have got different properties or fields, but in this case I am explaining it as a table because it helps to explain. So there is file offset, there is status flags, the one you used to use when you are opening the file, right? Status flags, and these will actually store per file and like per FD what are the flags with which the file was opened. Was it read only, read write, append only, all those kind of things, right? And the other column which we are interested in is the inode pointer. Okay, I'll soon come to what is an inode pointer because that is one of the other most important thing in kernel as a whole. Without that you cannot do anything. So once again we have a file offset. Here again we will have multiple rows, right? And these pointers that we have, right, these are nothing but they point to these rows. So let's say file 0 points to this one. Let's say we have opened maybe two different files or the same file twice using OpenSysCall, and it returned us two file descriptors 3 and 4. So in this case, so for the time being, let's consider that it was two different files, t1.txt and t2.txt, that was opened using two OpenSysCalls, and we will later come to this example of single file. And what it does is that this struct simply tracks what is the current file offset for a given file descriptor, right? Let's say it's something called 2, it's something called 10, right? As in when you use this individual 3 and 4 file descriptors, this will get auto incremented, right, by the number of bytes read. Then there are status flag, rd only, maybe this is also O, something else, some other flags that you use. It can be a or of multiple flags as well. And finally we have got the inode pointer. Let's say it's something called 101, 102. So that's the first level of pointer redirection that's happening from FD to this table. And now what are these rows, individual rows called, which describes this file? So basically we are describing the file descriptor and the file, right? At what position in the file the descriptor is pointing at. what are the status flags, which inode pointer it is, which inode it's pointing at, and things like that. So what is this row called? This row, these individual rows or these individual structs or kernel data structure that describes a file is called nothing but file description. Yep, it sounds extremely confusing. File description, file descriptor, but again, it is what it is. So a file description is the actual kernel data structure that represents an open file. It's not the open file descriptor that represents an open file. It does represent open file in some ways, but it doesn't provide all the full picture. A larger part of the picture or a larger part of the file information is provided by these individual kernel data structures that kernel uses to describe a file, which is called file description. It's also called a file entry, and this table is known as the open file table. And it is a system-wide table, right? It's not per process, but it's system-wide table of files. So now we know that every call to a open file not only gives us a file descriptor, but it also gives us a new entry in this the system-wide table of open files, which is called a file description. That entry is known as a file description. So whenever you make a call to the open syscall, doesn't matter if it's a different file or it's the same file, you will always get a new entry in this open file table, which is known as a file description. And this kind of answers us the question, how come when you are using two different open syscalls, irrespective of if it's the same file or a different file, how come the kernel is able to track the different offsets for the file descriptors, right? Because the underlying file description, which is backing this file descriptor, is different, and it has got this column file offset to track them, right? To track the different offsets. So that answers our one question, right? How come two different open syscalls are able to track two different file offsets for two different file descriptors? Now, what exactly is this inode pointer, right? So we know the file properties, right? We know the various file properties, but still we don't know where on the disk the actual file blocks are located, where the data is located. Like the file data is stored as blocks on the disk, right? But where are these blocks actually stored? What is the address of these blocks? What is the range of the blocks that's responsible for this file? You don't know these answers yet, right? Are there any file locks on this file, right? What is the type of this file? You don't know these answers yet. So for that, we have another table and a whole different powerful data structure. And the data structure is called inode, and the table that stores this list of inodes is called very intuitive, the inode table. And this has got tons of properties. Like each inode struct has got number of properties, but we won't go into those details. Inode in itself can take a separate video altogether. But we have got file type, we have got locks, and so many things, right? We have got a very powerful list of functions, pointed to a list of functions, actually a list of pointed to different functions, which is called the inode operations, but I won't dig into that here. The inode operations tells for a given file type what are the file system specific functions that can be performed on that inode. Similarly, file description has something called file operations list of pointers, which points to functions, which tells you for a given file system how to operate on a given file, because how you would access a file, how you would read and write to a file is very file system implementation specific, right? So how you would read and write a file on, let's say, ext4 is very different from how you would read and write a file on a FAT, let's say FAT32. So on Linux also we have various like different file system implementations, different file systems, and every file system comes with its own implementation of accessing and reading and writing files, right? So we won't go into that. So the inode table stores one more very important property which is worth mentioning, is that's the file permissions, whether someone has the right to actually read from a file or write from a file or do both or execute a file and those kind of things. So those permissions are also present in inode table. So what now happens is that, let's say this 3 and 4, as I mentioned, are two different files, right? T1 and T1.txt and T2.txt, and that's why we got two different file description in this table. So basically this 101 and 102, and since these are two different files, T1.txt and T2.txt, these two will have different inodes, right? And these inodes will give you, as I mentioned, all the things like file permissions, the actual physical blocks on the disk, the address of the actual physical blocks on the disk where the data is located. All those kind of things will be given from these inodes, and that's how your kernel functions will finally have access to the actual contents of the file. So these two level of redirections or pointer evaluations are happening to get to the actual data. There are more, but I won't go into those. There is a mechanism. How do you map a given inode to a file name, right? That's a very important thing. So you are not accessing a file by its file description or its inode number, right? You are accessing a file using a file path. And so how does a file path gets mapped, or a file name gets mapped to its inode? So this inode stays on the disk even when the file is not open. So all this file descriptor comes into picture when a process is trying to open a file or it has opened a file. Otherwise, these are irrelevant. File descriptor is irrelevant. File description is irrelevant. But the inode, it's maintained on your disk as a kernel data structure, right? Without inode, a file cannot exist. But then how do you map an inode to a file name? Again, that's a very big topic of discussions. Let me know in the comment section if you know already about it, and if you have used it ever for your debugging purposes. So another thing that's worth mentioning here is, so once you have opened the file and once the kernel has created this file description entry which points to an inode, the kernel doesn't care about the file name anymore, right? It doesn't care about the file path, file name anymore. You can rename the file, you can move the file to a different location. All the kernel knows right now is that for that file, it has a file description created and that file description points to a particular inode. That's all the kernel needs to read from your file. And this has got some very interesting implications. Once again, let me know in the comment section if you know what are the implications of this. The fact that kernel doesn't need to know the file path or name anymore once it has opened the file. So now, let's say I have opened one more file. Let's say it's called file fd5, right? fd5. And it has been allocated a file pointer which is, let's say, 50. And now what I have done is I have used this fd5 with a dupe system call, and it returned me fd6. So 6 is a dupe of 5, right? 6 is a dupe of 5. What happens then is a question. So in this case, since there was no new open system call but a dupe call on the fd5, fd6 basically is a clone of fd5, and what we get here is the same pointer, which is 50, right? So let's say 50 is pointing into this here, a row here, and the file offset for now at any given point of time, let's say, is 40, and it has got some rd only flag, and the inode pointer is, let's say, 110, pointing to some row here, right? Now this fd6 will also point to the same file description, and that's the key part. That perfectly explains why the file offset was being shared between both the file descriptors. It was being shared because they're pointing to the same file description, right? We know that the file description has one column for the file offset, and that's why the file offset is the same for both the file descriptors. And not to mention, since the backing file is the same, both of the file description is pointing to a single inode, and that's why when you were reading from fd5, the offset for fd6 was also getting incremented by the same number of bytes, right? How cool is that? So the kernel has taken care of everything for you, because if you need to reuse a file descriptor, why bother calling a system call once again? But now you need to be careful, because if you are using a duplicated file descriptor, you can, since the file offset is shared, you might end up reading from different portions of the file, which becomes more evident in case of processes, because there also the same thing happens. Now imagine we had another file fd, let's say something called 7, right? Now fd7, now let's imagine for a moment fd4 is this t.txt example. If this fd4 we got from a open call on t.txt, and fd7 also we got from a call, a separate is the keyword, call on t.txt. So we now have got fd4 and fd7. They are being used on the same file but using two separate open file descriptors, right? So let's say this is now pointing, fd7 has got a new entry now. This is pointing here, and let's say the descriptor is somewhere around 50. This was 43, this is 51, right? and some flags are there, and let's say yes, so some flags are there. And now coming to the inode, so we know that both fd4, which was pointing to this row, right, and the inode was 102, which is, let's say, here. And now we have got another file description, which is 50, which is also which is being pointed to at by fd7, and this is also pointing to the same file. So the file descriptions are different, right? The file descriptions are different. The file is same, file descriptions are different. Hence we are getting two offsets, and that perfectly explains why when we opened the same file using two different open system calls, we were able to track two different offsets via the two different file descriptors, because the underlying, although the file is the same, but the underlying file description is now different. There are two independent file descriptions created for those two independent open sys calls, even though the file is same, right? So now you have got two different file descriptions, but the underlying file is same. So since this is pointing to this 102 inode, and for fd7 is this, the file is same as fd4, there won't be a new inode, but it will point to this inode, right? And that explains perfectly, like the fact that the kernel decoupled file description from inode, it doesn't have to, like, the inode doesn't care about the file offsets and those kind of things. The inode only cares about the other stuff, like the physical blocks on the file, the permissions and all those kind of things. It doesn't care about the offsets and stuff. So that duty of tracking the offsets, the file, the status flag, and all those things have already been offloaded to the open file table, right? And that's where this decoupling helps us. That kind of explains us why two different open sys calls on the same file gives us two different file descriptors, which are actually different, and gives us two different file offsets, but we are kind of reusing the inode. We are not duplicating the inode. Now let's go to our final and third example of processes, how this works for processes. So now let's say we do a fork. P1 does a fork and it creates P2, right? And again the same thing, the P2 is basically our worker, which calls the worker function, and it also tries to let's say P1 till now has opened this file has this fd called fd3, the exact same example. P1 got a file descriptor called fd3, which is pointing to t.txt, and since P2 was forked from P1, by default when the process gets forked, it gets a copy of all the parent's open file descriptors. So if we see the process table of P2, this is the file descriptor, open file descriptor table of P2. What we will see here is in file ptr. So remember fd3 was pointing to this file description, which is currently at offset 2. So now it will have the 0, 1 and 2 file descriptors copied from the parent as usual. It will also get a copy of fd3, and that fd3 will again have a file pointer, but again it's a clone, right? Process 2's fd3 is pretty much a clone of process 1's fd3, the parent's fd3. So in this case fd3 was pointing to 42, right? The file pointer. So here too it will get the entry 42, the same file description, which means it will be pointing to the same, this one, as fd3. So P1's fd3, so P2's fd3 will also be pointing to the same file descriptor, right? So what it means is, although these two are different file descriptors, right? Again, the file descriptor number is same, but in reality the file descriptors are different, right? One belongs to parent, another belongs to child. We can have the privilege of having the same file descriptor number or fd number because the open file descriptor table is local to a process, right? It's not system wide. That's why we are saying it the per process open file descriptor table. But since the file that is being opened is the same, and the root of all the things, the open system call was called only once by the parent process, so the file description, underlying file description that got created is only one. So the fd3 of process 2, which was cloned from process 1, it also points to the same open file description, and hence the file offset is same. So back in our example, when what will read 1 byte using this FD, the parent's FD, I mean the parent's cloned FD. The offset got shared between the two processes for FD1, and any increment of offset done by the child persisted in the parent process, and that's why the parent got the second byte from the file. So overall, when we are accessing a file for reading and writing using nothing but an integer, right? At the end of the day, file descriptor, we refer to it as just an integer. In reality, it's not just an integer, it's this key to this entire world of redirections and pointer dereferences that's happening inside the kernel. Using that one integer, the kernel does a first level lookup on the open file descriptor table on the process. From there it gets a reference to the open file table, the system wide open file table of file entries / file descriptions. From there it can check the status, the file offset, and all those kind of things, and from there it gets reference to the inode pointer, and from the inode pointer it gets references of the actual blocks where the data is being stored. And each and every time you are reading something, you're writing to a file, all these things are happening in split seconds, right? In super fast, because that's how the kernel has taken care of things for you, and that's how everything works so seamlessly, right? Yeah, so that's what a file descriptor is, what a file description is, and what an inode is, right? So yeah, this is what I wanted to discuss in this video. I wanted to discuss about these different things that happens under the hood when you operate on files, and each of these things has got very beautiful and at times very interesting implications when you use them when you do file operations in your day-to-day life, which I shall discuss in my subsequent videos. But for this video, I believe this is it. I hope you all like this video. If you have ever if you have ever run into these low-level things while any of your debuggings, when you are working on something on your day-to-day job, any interesting thing that you ran into where file entry, file descriptor, inodes were involved, do let me know in the comment section below. It's always great to read these kind of things. So yep, that's it for this video. Thanks a lot for watching, and see you all next time.